So I'll be talking about things related to glasses and chaos. This work has been done by Lokesh, who is a graduate student at High Energy Physics IISc, and earlier graduate student in my group, Surojit. So the main reference is here, this archive, and then the earlier work in this reference. Okay, so just to set the stage, so the classical chaos we all know, so essentially is this divergence depending on slight change of initial condition, your trajectories go away from each other exponentially, and the rate defines this Lyapunov exponent. So this is the standard classical chaos. Now to sort of generalize quantum chaos, there is not a single definition. So for this purpose of this work, the particular characterization, which is not a very general one, works for certain models only, that I am going to use is this way. So the idea here is that if you look into this quantity which defines the Lyapunov exponent classically, then you write a Poisson bracket, this quantity in terms of a Poisson bracket, and once you write a Poisson bracket, you can write it in terms of commutator, assuming that it is close to the semi-classical limit. And once you write this is of course an operator, so this doesn't have as such a given value. To obtain some number, you do averaging over this quantity some way, and turns out the correct averaging is to square it and then average. And then if you are close to the semi-classical limit, basically if the classical system is chaotic, then this quantity will also be growing as e to the power 2 lambda LT, 2 because of the square. And you can define, and if you have such system, you can say that this is a characterization of chaos. Now for many body systems, general many body quantum system where there is no such obvious classical limit, even then what people do is that you just take two operators for the many body system, let's say two spin operators at x and z, or at two spin operators at two different sites, and then you just look into this commutator square average, and if in certain system this grows exponentially, then you define that system to have this quantum Lyapunov exponent. So sometimes rather than looking into commutator square, you look into a part of it. If you expand this quantity, there will be a part of it which is different from standard correlation function you look into in quantum many body systems or quantum mechanics, which is called the out of time order correlator, because this staggered ordering of this time here. Okay, so the time is staggered order. So this is called the out of time order correlator, and it indicates, so if this quantity grows this form, then this quantity decays in this manner. So now you can, so of course you can get this one parameter Lyapunov exponent, but you can extract another quantity also by using the same kind of correlator, but now looking at two operators in a local system with a local Hamiltonian, let's say two local operators which are separated in space. So let's say some operator at some position x equal to 0 and some another operator at some other position, and you look into this. So now it turns out that of course at a given position x equal to 0, this will grow because of the Lyapunov exponent, but since initially these two operators are spatially separated, there will be a delay to start this growth away from this point when these two operators starts overlapping, and that can define a butterfly velocity. So you can extract a velocity from this light cone. So these are these two quantities you can extract. So now why we study chaos in glasses, which is the topic of this paper. So now of course just here there are experts on glasses. So just to take the very basic ingredient for this talk, so what we do is that so what we do here is basically the idea is that these glasses are defined by this complex relaxation, where at high temperature you have simple exponential relaxation, but low temperature you start getting this complex multi-step relaxation with some beta relaxation and long alpha relaxation, and then there are some apparent divergence of time scale above the glass transition temperature. And for spin glasses or the infinite range model that I am going to discuss, this will be a true divergence. Now the picture of this kind of picture that you get of this is that very high temperature is the system samples and doesn't really see this ragged potential energy landscape classically, and if you go to lower temperature, then it starts sampling many of these metastable states, it starts sampling these minima, and it also starts sampling the saddle points. Okay, so you start sampling the stable and unstable fixed points of this landscape, and the idea is that maybe because it is sampling over these metastable states, these stationary states, the system classically could be very sensitive to initial condition, right? So maybe whether you start at a saddle or slightly away from it, it can have a completely different outcome. So there is a chance that in this regime your chaos might be very enhanced, and at much lower temperature again it will go down because you are only stuck. Right, so in fact that's what we found in our earlier work. So this is a model which I'll describe very briefly later. Basically this is a quantum spin glass model which is called a quantum P spin glass. What is plotted here is a chaos phase diagram as a function of quantum parameter and temperature, and what is plotted here is the Lyapunov exponent calculated in some way. And what you find that there is this glass transition temperature. So this model has exact thermodynamic glass transition and a dynamical transition at Tc and Td. However, if you look at the lambda L, it actually has a maxima which is indicated by this color above the glass transition temperature, somewhat above it. Okay, in fact, what we showed that exactly at this temperature you start getting the two-step relaxation, right? So this temperature exactly coincides with the onset of two-step relaxation. And later works actually showed that in fact if you look into if you calculate the complexity of this potential energy landscape, basically you count at that temperature how many stationary points you are sampling, that also peaks at that temperature. So that means where you are sampling many more of these stationary points, there your chaos become enhanced. Okay, so the question is that this is about Lyapunov exponent. What happens to information propagation, the butterfly velocity? Yes. Yeah, it's a h bar that I am varying. So let's say I can vary h bar. Okay. Okay, so now so let me just discuss quickly because I have very not much time left. So basically the model that we look into is two spin glass models. One is called the Sazdevier model, which has some infinite range spin-spin interaction. So both are infinite range model. One is quantum P spin glass model and one is the Sazdevier model. Both of them have some random interactions, and these two models are both solvable in the large n limit, where n is the number of spins basically. Okay, but these two models have different dynamics. This has some SUM, this is some SUM spin model which has some different quantum dynamics from this model which is defined by this thing. And in both this model you can vary a parameter, the quantum fluctuation parameter, which is this S, and in this model it is gamma. So these models has many rich phase diagrams. So the idea is that how chaos is affected by this complex dynamics and non-trivial symmetry breaking, like replica symmetry breaking. So now to generalize this model to look into spatial information propagation, yeah, I'll finish in 1 minute or so. So information propagation, what you do, you make a lattice generalization of this model. So imagine this infinite range model as quantum dots and you put them on a lattice. So you can write down the model. And it turns out that these models you can solve using some large n methodology in terms of these correlation functions. So this is the phase diagram of the Sazdevier model. So basically there is a paramagnetic phase and there is a spin glass phase. Now this spin glass phase is some replica symmetry broken spin glass. There are different kinds of paramagnets here. So at high temperature some local moments, and more interestingly at low temperature some spin liquid that you see. The P spin glass phase diagram is less complicated. It has a paramagnetic phase and a spin glass phase. The question is what happens to this the information propagation velocity across this phase transition. So to do that you calculate a quantity, this kind of out of time order correlator, and this can be calculated using some Keldysh formalism is kind of involved. And you have to do some diagrammatics and all. At the end of the day you can extract this butterfly light cone that I showed earlier, and from that you can extract a butterfly velocity. So let me just discuss this result and I'll end. So basically what you find that if you are let's say if you are going into as a function of S, so if you have fixed a temperature and you are trying to look at this butterfly velocity, so then so this is at small s is the paramagnetic state. So initially it increases and then it reaches a maxima and then it undergoes a minima exactly at the spin glass transition, and again in the spin glass phase it increases like that. So there are some asymptotic behaviors that you can extract here, but the main point is you still see a maxima above the glass transition temperature, and probably you imagine that the complexity, something is happening to the glassy complexity there. A similar feature you see in the P spin glass model. Now, if you look into this as a function of temperature rather than spin, then what you find that in the Sachdev-BA chain, the Sachdev-BA model, there is actually no maxima. Like I showed earlier for the p spin glass, as I showed that there was a maxima above the glass transition temperature, so here it doesn't appear. So this basically suggests that you have very different evolution of complexity as a function of quantum fluctuation versus thermal fluctuation in this model. Okay, so so this probably related to some the fact that you have a maxima is related to this complexity, but the evolution of the complexities are very different. So the main message is that that there is probably some interesting relation between information scrambling and the glassy complexity, some dynamical quantity and some quantity which you understand in terms of landscapes. Okay, and basically it is enhancing the chaos at an intermediate temperature, and it is apparently detecting the onset of complex relaxation. Okay, so with that, I thank you for your attention. Yes. Yes. Yeah. So in the actual system, you can tune it different ways. I mean, basically, it's an angular momentum scale. So you can tune it by tuning some temperature scale by effectively kinetic energy. Like you change the scale of momentum and the position, you can tune it. Yeah. Mm-hmm. Yeah. Right. It's finite temperature. Yeah. Yeah, so this general phase diagram that I showed earlier, so let me not go back into it because it will take some time. So general phase diagram you can study at 0 temperature, right? And you can just go across the H bar, right? So that will be a quantum. So these models have all of them have a quantum phase transition. And there also you see some features, although it is most interesting in the thermal case where you have this complex dynamics.
I have a oh.
Yeah.
So in most of the cases that I have seen, the ODOC seems to saturate. It doesn't really divert or anything. Are there systems
Yes.
where it actually?
No. So these systems also it saturates eventually. So the way we are calculating it cannot capture the method of calculate this field theory calculation cannot capture the saturation part. So you only extract the growing part, and also the point is that the saturation time in this model is 10 to infinity because of the large n limit, but it will saturate for finite n. Yeah.
About the difference in the usual transport in these two models, like the regular 2-point spin-spin correlators?
Yeah, they are very similar. Actually, so both of these models, as I showed earlier, that when you have this two-step relaxation onsetting, then you see this maxima in Lyapunov exponent. So it turns out that if you look at 2-point correlations, they have very similar feature that that at high temperature they are simple exponential, then you have a complex relaxation. So from that perspective, these two models are not different. But if you look into this Lyapunov exponent and butterfly velocity, they seems to be different.
I see.
Yeah.
I see.
But transport, real transport, you have not studied. Like you can study in this model diffusion constant, which you have not studied.
Yeah. So,
Yeah.
but the conserved quantities are similar in both the
They
cases?
are both, no, they are I mean, they are different, but both models have conserved quantities because SUM and
Okay.
other case you can define some particle density or something.
I see.
Yeah.
So if there are no more questions, let us thank the speaker.